Complex numbers are numbers of the form a plus ib, where a and b are real numbers, and I squared is equal to -1. Okay? So that has the immediate consequence of all real numbers also being complex numbers. They just have b equals 0. And 0 certainly is a real number, so b certainly can be 0. So all real numbers are also complex numbers. The complex numbers are defined simply from this, along with the simple operations of addition and multiplication. All right? So addition is obvious. Multiplication, of course, goes like this. All right, we have a distributive property for addition and multiplication. So that allows us to write this as then we'll use the distributive property again. And then we're going to use this additional property all right, to complete the multiplication operation. Okay? So from this, we can see that the product of any two complex numbers will also be a complex number. All right, in addition, we have subtraction and division. You can divide by any complex number other than 0. The way that that division operation takes place is easiest to see by first introducing the so-called complex conjugate. All right, the complex conjugate of a plus bi is a minus bi. All we do is we change the sign of the I part. Okay? Now, one very useful property about the complex conjugate is that if z equals a plus ib, then z times z complex conjugate would be a plus ib, a minus ib, which of course we get difference of two squares. We get all of the familiar algebraic manipulations that we have from real numbers carried over to the complex number system. So I would have difference of two squares, a squared minus ib squared. But since I squared is equal to -1, this is simply equal to a squared plus b squared. Now, a squared plus b squared is a real number that is strictly greater than 0 unless z equals 0. Okay? And here is where we get the issue with 0. We're not going to be able to divide by it. So let's say that I wanted to divide. So I wanted to find z such that 2 plus 3i times z equals 7 minus I. All right, so what I'm going to try to do is undo multiplication by 2 plus 3i. All right, I'm going to divide by 2 plus 3i. So I'll have 7 minus I divided by 2 plus 3i. And now what I'm going to do, essentially because of this nice property that the product of any complex number and its complex conjugate is a non-negative real number, I'm going to make use of that by multiplying here by the complex conjugate of the denominator. When we do this, the numerator, of course, will be able to complete by FOIL, but the denominator will simply be the non-negative real number, 2 squared plus 3 squared. Okay, and so then that gives us 14 minus 2i minus 21i. So that's minus 23i. And then it's going to be plus 3i squared. So that's minus 3 divided by 13, which is 11 minus 23i divided by 13. We can, of course, verify that that works simply by multiplication. So I could say 2 plus 3i times 11 minus 23i over 13 is equal to, well, I'm going to have to use FOIL. All right, so I'll get 22, and then it's going to be minus 69i squared. So that's plus 69, right? And then it's going to be minus 33i minus 46i. Or sorry, plus 33i minus 46i, all divided by 13. So this gives me 91 minus 13i divided by 13, which indeed is 7 minus I. All right? Now we have some other nice properties of multiplication and division that we'll find by making use of this a squared plus b squared. All right, so let me get rid of this check right here. And given any complex number, including 0, we're going to define the modulus of z, given by a plus bi, is written like this. It's written with absolute value symbols, like that. Okay? The square root of a squared plus b squared. All right? Now it turns out that if you multiply two complex numbers together and you find their modulus, let's see what happens. If I square that, I'm going to get z1, z2, z1 complex conjugate, z2 complex conjugate. And then I could move those around. z1, z1 complex conjugate, z2, z2 complex conjugate. So this is the modulus of z1 squared times the modulus of z2 squared. All right, so that tells us something that looks fairly obvious. The modulus of a product of two complex numbers is the product of the moduli of those two complex numbers. All right, but let's look at that here, okay, in this particular problem. The modulus of 2 plus 3i times the modulus of 11 minus 23i all divided by 13. Well, let's see, it should be the square root of 50. All right, or 5 times the square root of 2. That is not obvious at all from here. But let's see what happens. All right, so I'm going to get the modulus of 2 plus 3i is the square root of 13. It's not 13. It's the square root of 13. The modulus here is going to be the square root of 121 plus 529, all divided by 13. All right? So let's see what we get when we add all these up. So that's going to be the square root of 13 times the square root of 650 divided by 13. But that's the square root of 13 times the square root of 13 times 50. All divided by 13, cancel, 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 which is 5 times the square root of 2, exactly as it needed to be, because the modulus of 7 minus I is the square root of 50, 5 times the square root of 2.